Okay, hello everyone. So I'm here to present the work I've been conducting actually for the last few years. And I'm going to focus in particular in three specific publications that have resulted from this work, but we have more submissions on the way. So this is a topic that is continuously evolving, I would say, and is getting a lot of attention. So to be precise, of course, there is the last few years, ML systems have achieved incredible performance across a domain of applications, right? Not even related to image or speech. There are even real world applications that we have observed the last few years. And one pillar behind this success is essentially what we call neural networks and deep neural networks, which are essentially just multi-layer neural networks. However, as is relatively well known in the community, is that neural networks are not a silver bullet. They don't solve every problem. And in fact, I'm here to argue that there is another class of function that relies on polynomial expansion that can do at least as well or even better than neural networks in some particular tasks, as we will show. And to be more concrete, the question that we started studying this polynomial expansion was, can we use such high degree polynomial expansion for approximating high dimensional target distribution? Why high dimensional? Because that's what most machine learning systems care about nowadays, whether it is for audio or NLP or any other application domain. So here are some visual results from the end, just to give some positive outcome and answer to this question. And in A, you can see both A and B are actually some applications we do in the paper that was just accepted into NeurIPS and will be presented in a month or so. And it's conditional generation with polynomials, where one variable is the typical noise we use in the generative models, and the other one depends on the task. For instance, in A, it is the edges that you see in the first row, while in B, you have the attributes as additional variables. And the impressive thing is that we can synthesize both of those with what I will explain as polynomial expansions, which are a different class of functions than neural networks. So let me start from the beginning. So machine learning, we usually care for approximating one signal that has at least one input and at least one output, right? So this is the setting I will be focusing on. And you can denote this as learning a function g from a d-dimensional input that I'm going to denote as zeta, and then an o-dimensional output, right? So neural networks are popular ways of doing this, but what I will do today is slightly different, and I will capture we will design and present methods of capturing such high order correlation using tensors and polynomial expansions. Just 3 slides of notation before we get into the main polynomial expansion. The first one is Khatri-Rao product. It's not important the details of equation 1. I have just provided this example to show you that this is slightly different than matrix multiplication, but in the same same vein as matrix multiplication or Hadamard product. It's a way to do product between matrices. And why is Khatri-Rao important? Because it is required in tensors. Tensors, you can think them as multi-dimensional arrays where the order of the tensor is the number of dimensions. For instance, you can see a third order abstract illustration in the screen. And then the second tool we are going to use from tensors is the MODEM vector product that is denoted in equation 2. And the last tool that we are going to use is the Cp decomposition, which basically is a way to factorize any tensor W into a sequence of low rank components. So the reason I presented the Catry-Rao product is what you can see here, that it's used in the Cp decomposition, which will be a critical tool that we will be using for the tensors in polynomial expansions. So starting with polynomial, yep.
What was the circle with a square?
Circle with a square.
The circle dot squared. This sort of new product. What does the square on it mean? The power 2.
Circle with a square. I'm not sure what.
By square I mean the power 2.
Sorry, it means Catry. Yes, that's a good point. It means Catry-Rao product. So this essentially means U2, U3, U4, U5 until U capital M. Each UI is connected with each other UI with a Catry-Rao product. So this is essentially a shortcut. Sorry, this is a shortcut for writing U2, Catry-Rao U3, Catry-Rao U4, and so on.
Okay.
So this is like very standard notation in tensor literature. I'm just introducing it up front to explain what we will be doing later. And if like this is just some tools I will remind you when we need them, but this is just a very abstract thing. Tensors Cp decomposition is 2 tools that we will use, and this product we will just use it to convert to Hadamard product, which is element-wise product. So starting with polynomial expansions. So assume for the time being that we need to approximate one scalar output, right? So I mentioned that the output in general will be O-dimensional, but assume that for now we care only for the tth element, right? So then equation 3 gives such a polynomial expansion of some arbitrary degree n. So the way that this is captured is there is, of course, some constant factor. Then there are the first degree correlations, then the second degree, and then here are captured the nth degree correlations. So here the WTIJ, WTI, and here the WT with all the indices is just learnable parameters essentially with the machine learning language. So if you collect all of them together, you can construct tensors. And of course, these tensors have an increasing number of dimensions, right? So here, for instance, we have 2 dimensions for this tensor W1. So essentially, this is a matrix. So T is 1 dimension is for the output. So each output has its own dimension, and I for capturing the first order correlations, and so on and so forth, right? So this one, for instance, has 2 T and then IJ, 2 indices for the inputs. And you can imagine that as we increase the degree, these dimensions also increase, which makes it harder to write down in this format. So I'm going to basically just construct them in a way that we use the modem vector product. So equation 4 is exactly like equation 3. I just used more compact notation, right? And then we started with the T element, but we can stack all of them together and obtain equation 5. So equation 5 is very compact. It might seem a bit mysterious, but essentially it's just equation 3 for every T element and written with tensor notation. So one guarantee that we have is that from Stone-Weierstrass theorem, a polynomial can approximate any smooth function, right? So which means that with equation 5, we could, for instance, approximate the target signal that we want. Of course, as I mentioned before, one problem is that Wn is of increasing degree, right? So, sorry, is a tensor of increasing order. which means that if we want high degree polynomials, as I promised in the beginning, we would need to pay a lot of penalty in terms of parameters. So it actually is exponential with respect to the degree of the polynomial expansion. And this is the exact expression. So D, I remind you, is the size of the input. N is the size of the polynomial expansion we want, right? So this number of parameters is prohibitive for implementing in any modern machine learning framework because it cannot fit in GPU and express high order correlations at the same time. So one reasonable solution would be to use what I introduced a few minutes ago, which is Cp decomposition or any other standard decomposition, and make each tensor Wn low rank. However, this has two problems. Number one, it still is exponential. And number two, it does not share correlation across different orders of approximation. What does this mean? This means that, well, this tensor W1 and this tensor W2 do not need to be independent, right? In fact, if you think of Taylor expansion, this would be something like the first derivative, this would be the second derivative, and so on, right? This, they are not independent. And this is just the second and main reason that we have modified equation 5, or rather we have tried to implement equation 5. And this is the contribution that now gets us into the first work, as I will present shortly. So basically what we have used is a coupled Cp decomposition. So this means that we use Cp decomposition, but in a way that some of the factors of the decomposition, so essentially the matrices, if you remember this slide I presented, are shared. So the first degree and the second degree share some of these matrices of the decomposition. And to demonstrate this, let me break it up and focus on the case of n equal 3, just because it's easy to write down the polynomial expansion for this small degree. So equation 6 is exactly a polynomial expansion of degree 3. And then what we care about is W1, W2, and W3, right? These are the learnable parameters. Zeta is the input. For instance, if we're doing image recognition, zeta would be the input image. If we are doing image generation, zeta would be the typical noise that we input in the generative model. So to implement equation 6, we need to find a way to reduce the parameters, which are W1, W2, W3. Beta is technically also a parameter, but since this is the bias, a constant factor, and in fact here it's a vector, we don't want to do anything to factorize it or to make it to reduce it even further. So I'm going to present next what is probably one of the critical slides for getting to the polynomials. So we do the Cp decomposition with factor sharing, right? And here is the scheme that we are using. So for W1, we set it Cu1. For W2, we assume that it decomposes in this additive correlation, W12 and W13. Even though the indices seem a bit confusing at the moment, it will make sense when I present the hierarchical structure and why is it 1, 2, and 1, 3. And then what we do is that we apply a Cp decomposition in each of these two tensors independently. So this results in these two matrices. Actually, they should be transposed. This corresponds to this, to the first one, and Cu3, U1 corresponds to this matrix. And then for the third degree, we use a simple Cp decomposition, and this is the result. Why? The reason I have used some symbols as shared, for instance, C's here, is not is something that we did by design in order to obtain a hierarchical structure. And to give an intuition about these symbols of 1, 2, and 1, 3 here is that essentially these are designed to capture the interaction between layer I, so the first index, so layer 1 here, and layer J, which is layer 2 here. So this W1 tensor is essentially capturing the correlations of first and second degree, and this the correlations between first and third degree. And the reason that we have used this sharing protocol is that it will allow us to get something that looks a lot like a neural network, but is actually a polynomial expansion. To explain how we can get from this to something we can implement with standard deep learning frameworks such as PyTorch, let me first explain one lemma that is critical, which basically converts...
Can I ask another question, please?
Of course.
You go back a slide.
Yep.
So am I right in saying C is a tensor?
C is a matrix. C are everything actually here is a matrix.
Okay.
All of these are matrices.
Okay. I think I'm a bit lost. Could you just start from the W1 and say what that equation means and how it's obtained?
Yes. Okay. So you're absolutely actually correct. So we started from here, right? Yeah. And then what I promised would be that I would factorize W1, W2, and W3. So then what I did was that I factorized them, but in a specific way, right? So this is a matrix. Do we agree? So I just use a matrix decomposition and factorize it in this way. Now, this is a tensor here, and I decompose it into two tensors. The Cp decomposition can be written in a matrix form, and this is where the Catry-Rao product comes into play. Because if you write I take this as example, and I apply Cp decomposition, then I can matricize essentially this tensor, and what I obtain is this result. So if let me backtrack a few slides actually. So I wanted to decompose a tensor W to a sequence of low rank components, right? So then I can apply Cp decomposition, which is essentially what you can see for a third order tensor in the screen, right? So the schematic gives the Cp decomposition of a third order tensor. And then what I can do is collect all these CIs, right? Each of these C1 is a vector, C2 is a vector, CR is a vector. And then I can collect all of them together and make a matrix C. Then I can collect B1, B2, BR together and make a matrix B. I can collect A1, A2, AR together and make a matrix A, right? And then essentially the matricized format of W can be written as the Catry-Rao of these two products. Actually, it's technically the matrix multiplication and then a Catry-Rao product following this formula. But this is a standard way of writing the Cp decomposition in a matrix format.
Okay, so do the U's in that equation on the second bullet point, do they correspond to the A's and the B's in the image below?
Yes, so actually I used slightly different notation here, but for instance, you could, depending on this index, so the dimension that you do the matricization over, so the way that you can matricize a tensor is that you can keep one of the dimension and then essentially flatten all the rest of the dimensions, right, to the second one to make a tensor, like an arbitrary tensor, a matrix. And then depending on the dimension that I keep fixed here, these matrices emerge. So for instance, if let's say C1 would be the first dimension that I matricize over, this, the schematic would result in C matrix multiplication B Catry-Rao A.
Okay. Would this be a fair summary that you've got tensors and you want to flatten them out into component matrices that then when you do this fancy product on those matrices, you get the tensor back?
Yes, but actually, okay, I only disagree with the last part is that the goal is not to get a tensor back. the right part, both the left part, so this is a matrix and this is a matrix. So applying Cp decomposition is one thing, but actually another thing is converting both of them, both the original tensor and the Cp decomposition, into matrices.
So how does the W1 relate to the Kirtley W?
The W1 and the W have the same elements, right? It's just that it's the same. You can think it as how a matrix relates to a vector, right? So if I vectorize a matrix, it has still the same elements. It's just in a very long way written as a vector instead of two-dimensional.
Okay, I think I'm getting a rough idea now.
Is the exact equivalent for high-dimensional tensors.
Okay, all right, thank you.
You're welcome. So, okay, recap for everybody else if you weren't following the last few minutes. So we are using again Cp decomposition, and in fact we care about the matricized version of that, which can be given by this formula, and this is essentially exactly the formula I have used for applying the matricized version in the slide I'm going to go now. Here. And then I'm just going to convert this Khadri-Rao product into Hadamard products. Why? Because Khadri-Rao does not, I think at least, does not exist in PyTorch or does not exist in other deep learning frameworks like Chainer that I was using, or MXNet, and so on, right? So, and also it changes the dimension of the image, while Hadamard product is just element-wise product that leaves the dimensions exactly the same. So this lemma is something that we proved in the first work of the series. That basically is equation 7. So given some matrices AN and BN that have particular dimensions, so you see that these matrices have actually their first dimension the same. Second dimension can be different, and then we have this very particular format of Khadri-Rao products AN and Khadri-Rao products BN, matrix multiplication of those. Then this equals the format of Hadamard products between A1 transpose B1 transpose B1, and in general AI transpose with BI. And this is actually the equation that we use in this. So I presented equation 6. What I did then was to factorize W1, W2, W3. And this is the format. So we should ideally add all of them together. And then we apply directly this lemma to obtain Hadamard products. And this results in the following structure that you can see here, that is actually very similar to a neural network structure, but with the difference that we have this symbol that is the Hadamard product. So very high level, this is a structure that we get if we have a particular factorization of the polynomial, and this is a polynomial because it has the Hadamard product. So if you are in the output here, so in the plus, by the time you do the plus operation, you have a second degree polynomial. By the time you do the second plus, you are a third degree, you have a third degree polynomial, and so on and so forth, right? In particular, this one was a third degree polynomial I was constructing, but then it turns out that this is very easy to implement in any deep learning framework. And in fact, we have implemented it in a couple. Both tax and deep learning frameworks, where U1, U2, and U3 are learnable factor matrices that arise from the Cp decomposition. C and B are also learnable parameters. C is actually also from the Cp decomposition, and B is your global bias. And you can implement this and learn the parameters using standard methods such as SGD or like your favorite optimizer or learning algorithm. Of course, this can be extended even further. So this is the arbitrary degree formulation. So it should be very easy to apply this formulation for constructing any arbitrary degree, because essentially it just takes the previous output, and this is a skip connection part, so it directly adds the previous output, and then it takes the previous output Hadamard product with some embedding of your input, right? And this is how you can construct any arbitrary degree, and then the final output is just an affine transformation with the matrix C and the bias. And what I was explaining this whole time was one particular Cp decomposition and set of assumptions we have done, right? If we change this set of decompositions, we can get vastly different architectures. For instance, if here, instead of this decomposition, additive decomposition, we assume another type of decomposition, we could another type of factorization, we could end up with a different architecture. And this is what I show here, that we have derived a couple of different decompositions that result in very different architectures from the original one. And with that, I would just say present a few empirical results that we have with this. So, of course, we know that if you try to learn any CNN without activation functions, you cannot get anything. This is not surprising. Essentially, it just learns first-degree correlations, right? So the activation functions are crucial in CNNs, but it's not crucial when it comes to polynomials, right? We can directly implement these polynomials, for instance, with the structure I demonstrated above, and we can synthesize the results. So these images are synthesized by a polynomial expansion where we don't use activation functions between the layer. Technically, we use a tan H in the output because otherwise the discriminator, because this was implemented in a GAN setting, was like fairly easy for the discriminator to separate the synthesized distribution from the target distribution. So all of these are synthesized with polynomials, and the same for these, where here, like the surprising thing is that we do like what is typically done in the generator, the latent space actually of the generator of a GAN, that we interpolate between two latent samples, and then we synthesize the respective images, and we can also interpolate between these two. And you see that the images synthesized vary quite smoothly, actually. For instance, here from the 4 to 1, they vary smoothly, both in terms of shape and in terms of color. And I'm not going to focus too much on the experiments, but essentially we have shown in the original paper, or it's like PAMI, like its journal extension, that you can get improvement on standard architectures, for instance, StyleGAN, on the maximum resolution that we could fit in our GPUs by using polynomials. And in fact, we believe that StyleGAN itself is a polynomial with activation functions and a couple of engineering tricks, and we explain this specifically how this structure can be casted as a polynomial. Then in phase recognition, we get, I think, is still state-of-the-art results in a couple of benchmarks with this polynomial structure, and also non-Euclidean representation learning. So this idea is something that we have been, it was the first paper on the series, and of course the code is currently open source, and we're happy to discuss if you have any questions on the first part, because I'm going to continue now for two more applications actually on generative models. Any questions?
Can I just ask another one?
Yeah, of course.
Being greedy with the time. My naive intuition would be that both for neural networks and for these polynomial networks, the function class is rich enough to like represent each other's functions. Does that make sense? Yeah, yeah. In which case, like naively, I wouldn't expect one to be much better than the other.
So this is a question that is open in the literature, whether like one is better than the other. I would say there are actually a couple of papers that point that at some cases it might be better to use polynomial. Actually, DeepMind has a paper about second-degree polynomials on this, that they prove that if you replace a fully connected layer with a second-degree polynomial, it enlarges the hypothesis space. So I'm not involved there, but like this was, I think, similar, like it was, they published this, they submitted actually to ICLR slightly after our first paper on the topic, where we constructed polynomials while they just focus on second degree. And in fact, there is recent work on the topic that prove that polynomials definitely enlarge the hypothesis space, which means that with the same expressivity, they can obtain better performance. But I would say the topic is not conclusive yet.
Interesting, thanks.
I will give in the end of the talk a couple of pointers, actually, for instance, this last paper, why I think this is very interesting. So moving into the next application, right? So this is on conditional generation, where we have a couple of attributes that we care about, and we want to synthesize images with these attributes. For instance, let's say that you care about the color and the digit, and then you synthesize, for instance, a 2 that is orange here. And of course, you have the input that is a low dimensional vector, for instance, the noise and the embedding, and the image is high dimensional in the output. And we care particularly for the topic of generalization and the inductive bias of generative models, right? So this has attracted attention recently, asking whether we could train a generative model without seeing all of the data classes, so all of the combinations, and what does the generative model learn? For instance, here you can see that this attribute of 2 orange is not seen during the training at all. Of course, we expect the generative model to synthesize 3 out of 4 combinations, but the question is whether it can synthesize the 4th. If we give this task to a human, we would expect that the human could easily understand and synthesize or draw the images of 2 orange, given these combinations, even given less combinations in particular. So we studied this and started by the conditional variational autoencoder, where we appended the attributes that we care in the input. But we observed that in every case, even if we append the attributes in the latent space, it could not synthesize the images very well. And the reason is that it essentially has the same prior over each class. And to alleviate this, what we proposed was to actually capture the multiplicative correlation here. So essentially, equation 8 is what we replaced the mean of these different latent space priors. So what is the multiplicative part is the one highlighted, so the rightmost term in equation 8, that captures the correlation between y1 and y2, where y is your label, for instance, the color or the digit number. And why does this work? Well, we noticed, and we actually do visualize in the respective paper, that it learns some priors. It learns to place the priors in a way that it can then synthesize even from unseen combinations. And one reasonable thing would be, does this scale? And the answer is yes, it does scale. For instance, of course, this is VI, so the results are not as crisp as generation with GANs. But we noticed that actually, even when the combinations, the number of combinations increase, or even when the data set change from NIST to fashion NIST, even to Celebi, you can still synthesize images that are not seen at all during the training, right? So, and here MLC, VI, CP, and T stand for Cp decomposition and Tucker decomposition, for the simple reason that we also use the same exactly trick and lemma I explained before, right? So we use a Cp or a Tucker decomposition on W12, and then we use this lemma to convert it to a Hadamard product. And then one reasonable question is, could we use additive interaction and not multiplicative interaction? Well, the question is, it depends. But if the task is hard enough, the answer is no, because if we want to synthesize some attributes that have a correlation, for instance, smiling and closed mouth, it's hard to achieve that with a linear combination. As you can see, the images on the top, they might smile, but the mouth is not closed, while the ones in the bottom that are with the proposed framework, they are able to synthesize smile and closed mouth. And this was the second line of second application that we have published last year. And this is the latest work where basically the idea was to generalize essentially the previous results for other types of conditional models. Because before we just used this conditioning for the prior, but the rest of the encoder and the decoder were regular neural networks. And the question is, could we use high degree polynomials and expansions instead for the whole mapping and not this trick just in the latent space? And the answer, of course, is affirmative, and assume that we have inputs Z1 and Z2, where, for instance, Z1 can be noise, Z2 can be a class or an attribute or a low resolution image in case you have super resolution. And we use exactly the same factorization tricks as we used in the first work, and we obtain equation 9. So equation 9 is very similar to the equation that I was discussing before. I think is equation 7, but with the difference that now instead of one variable, we have two variables, right? So essentially we have the previous term, the previous recursive term, that is a skip connection. And then the previous recursive term Hadamard product with this, which is embedding of the different inputs into a common subspace. And how this works is that you can see the highlighted green part here. This is essentially the first term. So if we start from x1, that would be the first order term. And now this captures the second order term. So essentially this term of equation 9. And this is precisely how it continues for every different term. So we have two parts, the previous part that is a skip connection, and the Hadamard product with some new embeddings, UNZ1 and UNZ2. And then we can apply this to a couple of tasks, for instance, edge-to-image generation, where edges are now the conditional variable Z2. Z1 is again the noise. And what is incredible is that this has been synthesized from a polynomial without activation function. Again, we use this tan H in the output of the generator, but we did not use additional losses. So even though this has appeared in the literature before, for instance, I think Pix was one of the first works that demonstrated how this mapping can be learned. It was always, or most of the time, they were either using additional losses, or in the case of Pix-to-Pix, additional losses like Pix-to-Pix, or other perceptual losses that were used in subsequent papers, or additional networks or complicated structures like bicycle gun, for example. Here, we didn't use any additional network. So you have one generator and one discriminator, and that's it. And no additional losses. So this is just learned with the gun loss. And you see that actually learning high order correlation, both autocorrelation and cross correlation between the two variables, results in a bit of variety in the generated images, right? So of course, I would say this is not, again, something that is perfect at the moment. I would say there is still ways that you can improve this. And we showcase that if you plug in, for instance, a diversity loss, you can improve the diversity of the images, of the images demonstrated here. But the scope was not to obtain state-of-the-art, but rather to showcase that by capturing these high-order correlations, you can indeed obtain quite a bit of diversity already with the gun loss. And the problem was not the mapping the way that the gun was learned, but we argue that the problem was the way that the generator was simply a neural network that was learning to ignore the noise, essentially. And of course, this can be generalized to arbitrary number of conditional variables. For instance, here we present with 3 variables in equation 10, and you can imagine we could add more of them. I actually think we released the code this week for this paper, since it's like recently published. And with that, I think I will just show one last result, which is the way the anime dataset that has annotated the hair and the eye color. And what you can see in A is every different combination. So each row depicts one hair color, each column depicts one eye color. All of these images in A are synthesized, by the way, not samples of the dataset. And in B, we keep the fixed Z2 and Z3 variables, so the conditional variables, and we vary the noise. So you can get quite a bit of diversity in the synthesized images. Again, the goal was not to demonstrate state of the art here, but rather to demonstrate that it generalizes beyond 2 variables. And with that, just to summarize what I believe, why I believe polynomial neural networks or polynomial networks without activation functions even are a promising area. And there is the first work is what I already referred to, which is a very recent arXiv paper that shows that it can enlarge the hypothesis space and is more expressive than regular neural networks. The second one is that actually we can achieve same performance with standard networks, for instance, ResNet, even by reducing the number of parameters, which is consistent with the first paper that shows that it can enlarge, it is more expressive. And you could also use it in modern architectures, for instance, self-attention and transformers. And the perspective of polynomials can help you reduce the computational cost, which was, I think, a paper in ICCV presented a month ago. Also, these polynomials can be very helpful in privacy-preserving applications that have particular reasons that I didn't go into details today. And actually, I think there are quite a few papers on this topic if you are interested. And of course, that the last topic for me is very exciting as well, which is that we have a lot of theoretical results on neural networks with respect to almost anything, but we don't know how many of those apply to polynomial networks. For instance, are deep polynomial networks, or essentially high degree polynomials, as expressive as second order, or are they like strictly a superset of the second degree expressivity? And of course, questions regarding the generalization performance of these class of functions have not been answered, or how we can learn optimize such polynomial networks. And lastly, one question is what happens with the training dynamics of these polynomial networks? Do they share the same intuition about this class of neural networks, and polynomials learn in the same way or not? This is something we haven't had the chance to study yet, but I think it's a very interesting question, because there are a lot of works that are published on the different biases, for instance, implicit bias of neural networks, but no conclusive results whether, or no studies actually on whether these generalize to polynomial networks as well. And with that, I would like to thank you for your attention. Any questions?
I think you had been answering a lot of questions in between.
I'm happy to ask more if there's time.
Go for it.
Yeah.
So in the decomposition stage, sorry to go back to that again, I just want to make sure I've got like a hot take essentially for what the purpose of that is. So is the idea to reduce the number of parameters while maintaining the same expressivity?
The goals are twofold, right? So number one, you are reducing the parameters. In fact, if you do the math, the parameters here, because of the sharing, are not exponential, they are multiplicative. So they are something like d times n instead of d in the power of n that we started with a regular network. But the sharing also is very particular, so as to allow one to get some performance some implementation in deep learning frameworks, and of course performance, because we didn't. So there are ways to do this reduction of parameters without implementing it in this format. So essentially something that is similar to a neural network. For instance, you could learn U1, U2, U3 independently if you wanted, or like a very different structure than neural networks. But we wanted essentially to use a lot of the results that the community has learned from training neural networks. For instance, how SGD hyperparameters work, how you use batch normalization or like initialization and so on. And to do that, we just thought of implementing it in a way that is relatively close to a neural network.
Right. Okay. And does it reduce the size of the function class?
This is an open question. We don't know.
Okay. Okay. Thank you.
Welcome. Yeah. Any more questions? Is it clear? So essentially, what I presented, again, moving back since I'm in the beginning already, is there are neural networks. They're incredibly successful, and I'm not arguing otherwise. I'm just saying that there is this alternative of approximating signals with high degree polynomial expansions. This is the takeaway message, if you want.
Could you explain a bit about your conditional VAE example, the intuition for why the standard prior is failing at the combinatorial generalization, and why your modification improves that?
Yes, sure. So essentially, in the VAE, you have you are sampling from, like, in the latent space, you sample noise from a Gaussian distribution, right? And usually you can assume that this is a zero mean Gaussian distribution, right? But instead, what we could and did was that we allowed the mean to not be zero, but different mean. And the way that we wanted it to be is to be a function. So the mean to be a function of the classes, the attributes that we care about. So the mean in this case is a function of y1 and y2, that are the two attributes, or the multiple attributes we want to generalize to combinatorial cases. And we modeled this mean as the right part of equation 8, where W1, W2, and W12 are essentially learnable tensors again.
So what is the reason why the standard, having the same prior for everything, fails when you try to generalize?
Okay, so I should mention the following, right? So there is one like well-known paper from Stanford that showcases that if you have like a lot of combinations, so I think they showcase this with classes. So in the case that you have more than 100 classes, even standard VAEs generalize, or at least that's what they show with toy experiments. But what we focus here is that we have, for instance, 2 attributes or 3 attributes, something like this, right? Not like more than 100. But what happens is that you don't, so essentially the reason that it doesn't generalize is that you don't capture the correlations between the two, right? So if you provide an attribute of color and an attribute of a digit, it doesn't mean that the method will learn on its own that these two can be combined in all different ways. It just learns that if someone asks me this color and this digit, I can map it to this image to pay less penalty. to minimize the loss. While if you, so I think this image demonstrates the use case the best, which is that if you have attributes that correlate between them. So for instance, if I ask the network to synthesize an image that has both a smiling attribute and a closed mouth attribute, then these two are hard to synthesize together because the network has not learned to correlate these two. It has learned that when I get asked smiling, I just output this. And when I get a closed mouth, this, right? But it doesn't learn on its own that I need to correlate these two and capture their interaction.
Right, thank you.
Να τον.
Yeah, any more questions? Any further on any of those? Are they clear? Like the ideas behind the polynomials?
All quiet in the Western Front.
Yeah. Okay.
All right. Thank you so much, Grigorios. It was really nice of you. And I'm sure, I think people would like to get in touch with you. Would you want to send us the presentation so I can circulate this?
Yes, of course. I can send you the presentation. Thanks everybody for your attention, and thank you for the invitation.